Hello and welcome to the Wi-Fi Digital Twin and Federated Learning demo by Politecnico di Torino and Eviden. The purpose of this demo is to showcase the use of a Wi-Fi Digital Twin for time-sensitive networks, integrated with a federated learning model to select the best traffic scheduling policy. Time-sensitive networking has gained traction recently, but open frameworks for simulating TSN over wireless are still lacking. To address this gap, we developed NS3-TWT, an open framework built on the well-known NS3 simulator. It simulates wireless networks with TWT, or target wait time, support. Our digital twin covers a multi-domain TSN network, each domain connected via an L3 switch that handles traffic with prioritized queues and time-gated control. Each access point is linked to the switch using configurable point-to-point links. In our TSN application, we define traffic flows between stations within and across domains to evaluate TSN performance under different traffic scheduling policies. The next animation illustrates a UDP traffic flow between two stations in separate networks, one in network Wi-Fi 1 and the other in network Wi-Fi 2. At the beginning of the beacon interval, all 8 stations across the 4 domains negotiated the TWT wake intervals with their respective access points. The sender station transmits the UDP packet during its scheduled TWT window. The packet is sent to the access point, then routed to the L3 switch, which forwards the packet when the appropriate gate opens. The packet is then delivered to the destination network access point, and finally, in the next TWT window, to the receiving station. We designed 4 scenarios with increasing numbers of industrial IoT sensors. For each scenario, we generated 500 problem instances of traffic scheduling. Each instance was evaluated using 9 different scheduling policies. Using our Wi-Fi simulator, we executed all instances and collected detailed performance metrics. We then selected the best performing policy for each instance according to a predefined objective function. The result is a comprehensive database that maps input features to the optimal scheduling policy. This dataset has been used as training data for an AI algorithm based on a neural network with a 193-dimensional feature vector as input, followed by 3 hidden layers. It outputs a probability distribution over 9 classes, the 9 considered scheduling policies.
To select the best traffic policy for scheduling flows in the 4 selected Wi-Fi domains, a federated learning model is trained and served through our MLOps framework. The MLOps framework offers AI as a service capabilities to the rest of the AICP management services, supporting the design, training, and serving of AI/ML models. This framework is built on top of Kubernetes, using Kubeflow as an open-source solution to deploy and orchestrate AI/ML pipelines in centralized and distributed environments. In this case, a distributed environment is recreated with 4 different clients, representing each of the Wi-Fi domains. Each client uses a dataset that describes the traffic characteristics of the corresponding Wi-Fi domain. To ensure the user isolation required in the federated learning environments, 4 different users and workspaces have been created in Kubeflow and MinIO. These workspaces allow to store data and develop and orchestrate isolated AI/ML pipelines per client. With this data, each client will develop an AI/ML pipeline, where a dense neural network model will be trained and used as an input for generating the aggregated federated learning model. The definition of each pipeline can be seen in the Pipelines tab of the Kubeflow graphical user interface. To generate the federated learning model, an aggregation server module, which is based on Flower Framework, will start aggregating the weights of each neural network model, following an iterative process based on the exchange of weights with all the clients during a specific number of rounds. To trigger this process, each client will run its AI/ML pipeline. When all clients have run their pipelines, the aggregation process starts for the selected number of rounds. Once the total number of rounds is reached, the federated learning model will be aggregated and stored in a model database based on MinIO. The model stored in the model database will be served through a model serving module based on kserve. This module will expose the model through an endpoint based on a REST interface, allowing to perform inferences over the model to get the model predictions. To showcase an inference process requested by client 3, a dedicated Python script has been developed. In this case, the best traffic policy recommended for the Wi-Fi domain associated to client 3 is a random policy. To summarize, this video has showcased the use of a Wi-Fi digital twin in time-sensitive networks, where a scenario with 4 different Wi-Fi domains has been considered. To ensure determinism, an approach to identify the best traffic scheduling policy in each Wi-Fi domain has been described. To address this aspect, the digital twin has been integrated with an MLOps framework to develop a federated learning model able to select the best traffic policy. The video showcased the operation of the MLOps framework by training, storing, and serving a federated learning model. The model produced was tested for a specific inference in Wi-Fi domain number 3, where a random policy was recommended.